All right. Welcome everyone to the next edition of Miton Times. Today we have the pleasure of having Bohumír Zámečník from Rossum. He's going to be talking about craft. Yeah, go ahead. He's going to be talking about character recognition. Right, the floor is yours.
Okay, thank you. So my name is Bohumír Zámečník. I come from Rossum and deal with reading the text. And today I will tell you something about how to find the text in various documents or photos or similar. So I chose some nice paper, 3 years old, from a Korean company which develops the Line application, which is a popular messenger in Asia. And they made so-called character region awareness for text detection, or in short, craft. And it is a nice bottom-up approach to detect text. And so let's start with some appetizer. So this is what it can see in the images. And it deals with the harder problem of finding text in scenes, even though if the text is not straight, it can be with perspective, it can be curved in different ways. And this is what it sees, and this is how it bounds the text in the result, and some more difficult examples. And now we can talk about how this can be done. So let's first start with the problem of text detection. So we have an image, and on that image there is some text, and we want to find where the text is located. Yeah, and now the thing is how to represent the text. Yeah, so there are different ways how to annotate the text so that we can train, evaluate, and so on. And one possibility is annotate the individual words, or we can even annotate the individual characters, or possibly even pixels. Yeah, and so it is possible, simplest, just to draw some axis-aligned rectangle or oriented rectangle, or possibly some general quadrangle, or even some polygon with like more complex polygon. Yeah, and there's a cost in annotations. So like if you go into more details, it will get more costly. And so there are datasets that which have annotations for words, but typically there are no annotations that go deep into individual characters or even pixels. Yeah, and for word annotations, which are most common, there's even a problem that sometimes it is not even clear where the boundaries between words should be. Yeah, so this method tries to use the characters as the basic element of text. Yeah, and it tries to find individual characters and then link them together, bottom up, to make fragments of text or words. And why text detection is even useful? So, for example, if you open Google Translate, want to translate some, I don't know, menu in some strange language that you don't know, you just point your camera there, and it needs to find the text and can translate the text and maybe draw characters in your language that you know. So it's instant translation. It can be image retrieval. You have a lot of photos of books, and you want to search there. Yeah, or document parsing, which is something closer to what we do in Rossum. So we have documents, and we want to find the structure, what is inside, and so then we can find important information there, and even recognize the individual characters into text. It can be useful also for navigation of self-driving cars and many different ways. So let's somehow check what has been done before. So before deep learning, there were like some specially crafted features. I will not go into details, but there are even some work of people from ČVUT, from Czechia here. Then when deep learning became like big, people started adapting object detection methods for finding text. So they tried ways to do regression on bounding boxes, but they had to adapt because text is not some squares, but very long rectangles with different aspect ratios. And so there are methods that do these adaptations to find the text by regression of bounding boxes. There are approaches to do pixel-wise segmentation, where they try to label each pixel, is it text or not? And then possibly they find some blobs of text and they try to maybe split it into individual characters and then maybe find some bounding boxes around there. Then there are even methods that try to combine both text detection and recognition tasks into one end-to-end task so that they can utilize the information about recognizing characters. And then there are some methods that try to work with individual characters instead of words. And one of them is called word soup, and the authors of this method say that they got inspired by this method, which was based on a single shot detector, but it found only rectangular boxes, so it was not good for curved text. But there was an interesting way of training using weak supervision, and we will see that influence soon. So this is the architecture of the Craft model. It is based on a neural network that takes an image and predicts two kinds of score maps. As I showed before, there is one score that tries to say, hey, there is a letter. There is one character. And then there's a different score which says, hey, this is placed between two letters. And one is called region score and one is called affinity score. And so the network, it has some dynamic input shape, so it can accept images of different sizes. And then there's some backbone based on VGG16, which is even in 2019 a little bit outdated, but it is there. And then so they compress the image into some small resolution, and then there is something like a UNet where they do upsampling with some skip connections. And at the end, there are some classifiers for each pixel and in half resolution of the input image. Yeah, and plus they added batch normalization for the VGG backbone. And the whole network has around 20 million characters. And what is very interesting here, more than the network itself, is the representation of data. So they do not find the text just as some binary indicator map, but instead they try to find like a center and some kind of shape or size of each character. And it would not work well if there's just some delta function, some spike on the center, and they get inspired by networks for pose estimation. Yeah, and what they did was they took a 2D Gaussian function, or rendered a Gaussian into a square, and then they perspectively warp that Gaussian into a rectangle of a character. And so this thing encodes the center of the character plus its shape and size. And so this is the region score. And then for the affinity, which together like neighbors within a single word, they do something similar and make the affinity score. And so for the characters, they have little quadrangles, and for the affinity, what they do is they take the, I'll try to show here, they take two neighbors and they make diagonals, and those diagonals split the quadrangle into 4 triangles, and they took the upper and lower triangle and do that for the 2 neighbors, and then they joined the centers of those triangles to form another quadrangle. And this quadrangle, that Gaussian inside, represents the affinity, which is like very nice. Yeah. And but now the question is how to get those little quads here for the characters. And so the answer is they do the training in 2 steps. We don't have data, so what can we do? We cannot afford to annotate so much data. So let's synthesize data, right? So we can take fonts, we can take some perspective transforms or whatever, and we can render the fonts, and we know exactly where each character is located. And plus, with the transforms, we can also transform the bounding boxes that we know to get those quadrangles. And so with this, they were able to train some first model, to bootstrap a model that can detect text on synthetic text. Yes. And with this model, then they could utilize real data by finding the text in the real data, and then they were able to segment each letter, and for each letter they had the quadrangle, and they could draw a new ground truth. This is the pseudo ground truth. So they with some bootstrap model, they were able to make some pseudo labels for weekly supervised training. And here we can see that even though like the image is, the text, sorry, is a little bit like with some perspective, with the bootstrap model, they can find the rectangles, then they can warp them into a straight rectangle, and they have these region scores, and they can do watershed segmentation to split those characters, and they can get bounding boxes, and using the bounding boxes they can render those Gaussians. One thing is that at the beginning, as I can show you here, at the beginning the predictions are not so good. Yeah, and so they treat this uncertainty by multiplying those scores with some confidence, and that confidence is based on how well it can find the number of characters. So if the number of characters in the target matches the transcription, because they have also the text for that. So they can assign the confidence. So if it matches perfectly, the confidence is good. But if it cannot segment some letters, the confidence goes down. And possibly if the confidence is too low, they just skip it. Yeah. And so this is the watershed labeling of those region scores, so they can separate it. In some cases where it's not so easy to separate, they just split it uniformly and hope for the best. Yeah. And this is some example how it trains, and so they can repeat these steps and get the pseudo labels for each epoch new with better and better model. And as for the inference, if we have those scores as I showed here, or maybe the real prediction here. Yeah, so this is, for example, the region score, and this is the affinity score. So when we have those scores, we want the bounding boxes and how to get them. So there are different options. If we only want to get oriented rectangle at word level, what we can do is that we take the scores, threshold them, and make a union of these binary maps. And then we find connected components, and then we can draw some minimum oriented bounding rectangle. Or possibly we can just draw an axis oriented bounding rectangle, anything, right? And this is good approximation if we have some straight text, but we will see in the examples that this may be a little bit limiting sometimes. Then it is possible to split this into characters, as we saw by the Watershed segmentation here. And we can split the word box into rectangle box and do that maybe even when this is like warped into straight rectangle and then can be warped back. And then it is even possible for some very curved text to get the polygon for the whole word. And for that, they first find the oriented rectangle, and then they find some local maxima of the region score, and they connect them by this center line, and then they find the maximum height of the character, like this, maybe on that thresholded map, yeah, and take the maximum of them so that the letters have some uniform height that is covering all the letters, and then they just rotate that line to be perpendicular to the center line, or to the connection of two segments of that center line. And then those points make up the vertices of the polygon inside, and plus at the end they can shift it a little bit to the side so that the whole letter at the end or beginning is covered. And this way they can get the polygon, like refined polygon. And now the thing is about the data sets. Yeah, so for the first like synthetic training, they used some existing data set called syntext or syntax in the wild, which is annotated by quadrangles, has text annotations, and there is something like 800,000 images, each of them containing several text or several words. I'm not sure exactly, I could not find the information about the split sizes, but it will be something, I don't know, 15% for validation or something like that. I'm not sure. And it seems that there are multiple languages. And this was the main training data set. And for some fine-tuning, they use a few data sets from IGDAR, and they trained this 13 plus 17 plus syntax, and then another model only on 15. And then there are some more data sets that are possibly more interesting because they contain some cursed text, such as this total text, but there are problems. For this MSRA TD500, there are no text annotations, so that they cannot reliably do the confidence thing. And then for this total text and CTW 1500, there are only polygon annotations and they are not able to use them for training. So they trained only on this plus those two IGDARs. And actually for evaluation on those data sets below, they use this 13 plus 17. Yeah. And it turns out that when they use the big synthetic data set plus some tiny or small real data sets, the model works quite well on them. Plus, it can generalize even to those curved data sets where it hasn't seen before at all, right? And one thing is that this about the text content, and the syntax contained multiple languages or multiple scripts. Those two IGDARs were only in English, but IGDAR 17 was with 9 different scripts or languages and something maybe less than 9 scripts, including, I think, Chinese, Korean, and others. And this one contained 2 English and Chinese. Here I was not able to find probably English, maybe something else, and here's the similar. And these are the results. And they made the results separately for quadrilateral annotations and for polygon annotations and for models which were trained including text recognition. Yeah. And it turns out that on those IGDAR and MSRTD 500 datasets, their model was beating everything except one score of one data set, and it was very close. So it seems that it's quite good. And even though it hasn't seen this data set before, this one. And as for the speed, here they show something around 9 FPS. So that's something over 100 milliseconds per image. And the image sizes were something around 1000 pixels for the wider side. And probably on GPU, but I don't know exactly which GPU. And then they also evaluated on the polygon data sets where it was not trained on them at all. And it seems that it's quite good. Yeah. And even it is better or comparable on data sets where the other models were able to recognize the text. So it's quite good. And some discussion about the results. So it seems that this kind of representation, where it builds the words bottom up from characters, is quite good for robustness to different scales. So even though there's some perspective and one character is small and other character is big, it is no problem because it only looks at some small neighborhood, not the whole text. And it seems that I tried on one document with Moire, like photo of a screen of a computer, and it was able to find the text as well, even though they did not say that there were augmentations with Moire. And it seems that it generalizes quite well on unseen data sets, and it was trained on different scripts at once. And it seems that it works well when the characters themselves are separated spatially, such as for Latin, Chinese, Japanese, or Korean, where the characters are in some squares or small rectangles and are separated. But it is not as good on scripts where the characters are linked together, like Arabic or Bengali, because it just breaks the assumption that we can draw some nice bounding box around a character. But anyway, it can find the text, but it is not easy to separate the individual characters. So for word detection, it might be still good. And one thing is that even though we have some curved or distorted text, and we find the polygon or quadrangle, we can then do some perspective warping or some elastic warping or some other method, so that we get some straight text that we can then pass to the text recognition model, and that text recognition model can have like less work to read the text itself. It doesn't have to train so much on very distorted text. And it seems that if I try to compare it just by picking at some previous methods, that it is actually quite straightforward and simple, like no big magic. And still, the results can be as good as is the post-processing. Yeah, and I will try to show some examples in a moment. And when I just glance at the description of the network in 2022, I don't know, some obvious thing that seems to me is that the backbone could possibly be modernized using some modern convolution networks, or maybe possibly even some transformer or whatever. And yet we can keep the representation that this internals could be replaced, and then possibly the network can be even faster or get better quality. Might be some interesting experiment. And also what the authors write in the further work, they say it would benefit also from joint training with text recognition. And I could imagine that like with this model, you could do training where you pass some big image of the whole page, and then maybe you could pass some small image, and with some different head, you can read the text, and with this head, you can try to segment the characters, find the characters, and maybe it could help as well. And possibly what could be done is some like multi-resolution inference. So, I mean, if you have a big page, we could first try to find the text roughly with some small resolution, which could be done quickly. And then when we find some probable places of text, we can crop into them, and then we can take them in higher resolution and do one more pass on those crops and find the text more precisely. And it could be faster than if we predict it on the whole big page, which is mostly empty, in full resolution. I haven't tried it, but it might be. Actually, yeah, I think in some experiments we tried something like that, and it was a bit faster. Like if we took the crops for the same time, we could work in higher resolution. Yeah, but I don't have numbers at hand. And then there's a little problem with the oriented rectangles, and I will show in an example. And just some thought that this method is specifically designed for crazy curved rounded spiral text. It might possibly be a little bit of overkill for nice straight text in some beautiful, I don't know, PDF renders or whatever. But on the other hand, if you get just some scan with a book, like with some curves, or if you get a photo of a page with perspective, or the paper is crumbled, just with the same amount of work, you get support for that. No need to do anything else. Yeah. And it is possible to try that without writing everything from scratch, because the authors published a repo with the implementation in PyTorch, along with a pre-trained model, which is probably not only Latin. It looks that it supports also other scripts. And there is another repo which improves that a little bit and wraps that into a Python package, which you can just install via pip easily, right? And then there is also some rewrite into Keras, so along with converted weights into Keras format. And it seems that it is possible to load it even in the latest TensorFlow, even though in the requirements.txt they have TensorFlow 1 point something. So it's still working. Yeah. And some practical experience. So I took an image and resized that so that the bigger size is 1024 pixels. And on some recent hardware, it's working quite well. And the FPS, let's say, is quite close to what was reported in the paper. Yeah, and here we see results from the Keras implementation, which does not have the post-processing for polygons. So they are only the rectangles, oriented rectangles. And we can see that it is possible to, it can find text in like very perspectively distorted text, even though if the text is part of some logo, like here the pizza, but we can see maybe here I had some better example, but I removed that. Maybe we can see here that the minimum bounding rectangle is actually something different that we would expect. We would expect that if the text has some orientation, that all the rectangles would have the same orientation as the text. But if there is some text with like going down and going up, then the rectangle is like this. So there can be some improvement in the post-processing to put some knowledge about the texts so that the rectangles can be a little bit more meaningful. Yeah. And another example, this is some Chinese invoice from some public data set, and it can see we can see that it is trained even on Chinese, and it can read some Chinese characters. And here we can see that not all of them, but in the original feature map, there were all of them. So it's just a matter of the thresholds. Right? The features here were just a little bit weak and they did not get into the rectangle. But on the other hand, it is able to find characters which are in the stem and even here in the curved text in the stem. And in the original feature map, there were like dots around here. But since we don't have the polygon, the post-processing in the Keras implementation, it is not here. But anyway, like for this in, I don't know, 200 milliseconds, just incredible. And so that is it. And now you can ask some questions. Thank you.
Thank you, Bohush. That's really nice. If there are any questions online, you can just unmute yourselves and we should be able to hear you. And if there are any questions here, I can just hand you the microphone. So just raise your hands and yeah. Okay, so we have one.
So I'm curious, you mentioned it might be a little overkill to do this affine region for axis aligned text. Do you think that in case you would really want to detect just axis aligned text, not in the wild, there are more lessons from this architecture than just the backbone? Because then, right, the character boxes would be axis aligned. The affine connections between the boxes probably wouldn't be needed. What do you think would, in this case, be the main learning from Craft?
I think one interesting point is the way how it is trained, even despite the lack of annotations. Yeah, so this is something that we can apply to any domain. Start with some synthetic data, make a bootstrap model, and then go with some small amount of real data, make weak labels, and then rinse and repeat and get some better model with that. That is applicable anywhere. Yeah, and as for the like constraints on the boxes, it's mostly about the post-processing. The affinity scores, I think they should be there still, because they say how the characters are connected into words. So when an affinity between two characters is missing, it means that there's a space and we can cut it there, which is in itself, it's quite useful, right? Because what can we do even with straight text, whatever, when we detect the words and know that, hey, this is a space and nothing, we are not cutting in the middle of a word, we can take those word rectangles and take them all, for example, and put them into batches for the text recognition, so that compared to a situation where we have only the lines or some text fragments where we are not sure where to cut, we have to put the whole line into the text recognition model, so that the text recognition model has to support like very wide strips of text, high aspect ratio, and for example, if there's some RNN in that text, it has to go all the way through that, even though it's not necessary at all, right? So instead, we can cut it into words and then recognize the text in parallel, and maybe it can be even faster like that. So still, it might be useful with the affinity scores as well. And maybe one idea is that if we get some scan of a page that was just put into the scanner and without care to align it very well, or even if you try hard, it's still rotated a little bit. So you need, if you want to work with the text or with the layout well, you need to rotate it properly. Or if you have a photo with some perspective, it would be good to straighten it, rectify that into a rectangle. But if the orientation of the page itself, it typically depends on the text. So you evaluate it by the text. If the text is upright, then the page is upright. Maybe even the print is a little bit rotated. So if you check the paper, you will get a wrong result. But the text is the main thing. And if you take the page or the photo scan, put it into this method, and just take, I don't know, the centers of these region score blobs, then maybe the affinity, and you make some like lines, then you can use this information to fix the orientation or the perspective itself. It will be some very good feature to fix this. So if you think that it's only a matter of rotation, you can try to find the best angle that makes those lines of text straight. Or if the page is maybe like to the side, you can see the lines are going like kind of horizontally, so that you can rotate it in another way, right? And if you cannot rotate them so that they are all parallel, it means probably there will be some perspective, so that you can try to estimate the perspective transfer for that and warp it. So it could be used even for tasks like this.
Nice, thank you. So are there any more questions? Right, I have two, to be honest. So the first one is, you mentioned a lot of ideas about like where to go from here. Do you know if anything has been done from this? Because like multiple resolutions, like feature pyramid networks or self-supervised pre-training or something like that, I imagine could be done as well. So do you know if there has been any continuation?
To be honest, I didn't have so much time to explore the whole field of text detection. So I was just happy that I was able to find a method that is quite nice and that I could try, and or that we could try and get some results. And for sure, there has been some development, but to be honest, I was not able to check all the papers.
I understand completely. Thank you. And the other question I had was, at the beginning you mentioned that there were some methods from object detection influencing the text detection, right?
Yes.
And did it go the other way around as well? Because, for example, the Gaussian estimation, I think, could be used directly in object detection, like drawing the bounding box around some object. It could be done with like the Gaussians as well. Do you know if it? Have you seen it anywhere else? Because or did they come up with it? Because
you mean using the Gaussians here? They explicitly state that this was inspired by some papers in pose estimation. So when they have a photo of a video of a body, they want to find the skeleton lines of the body, the interesting points and lines in the body. So this was inspired by those methods.
Nice. I didn't know that. Thank you. So any other questions? Again, if you're online, you can just unmute yourself. We're going to hear you. Or just type the question. We can read the chat. All right. In that case, I think we should thank Bohush again.
Thank you.
And there's just a small bit of information. We don't have a speaker confirmed for the next time. So because of holidays and summer. So if any of you are interested in giving a talk, just reach out to us. Otherwise, we will post the information on meetup.com as usually. So looking forward to seeing you next time, and thank you for coming.
Okay, thank you.